Exactly, that's what I'm saying. Okay, so you, so I know. That's actually not good.
Yeah.
Oh, yeah, yeah. Someone's having to.
Yeah.
If your first year is just do that. Just do that first. That's what I'm. Both first years.
What's the farmer? It's like, yeah, like there's a farm. Like, they don't teach us in capitalism. Like, you're.
Just too bad.
Well, for you, I'm gonna go with that. I'm gonna like. Is it Euler?
I've heard it both ways. I'm gonna say.
Okay.
So today we're going to talk about a process that it's going to feel like linear approximation. Really, we're just using the derivative function to help us map out where we think where the original function is going to lie. So I'm going to first show you kind of like a visual connection to this, and then after that, it's going to just feel like we're creating a table. We're going to gather a bunch of information, and it's not going to be hard. It's just a little bit tedious. But you won't get to use your calculator on the quiz. So after we go through a couple of these it shouldn't feel that difficult. So I crossed out 7.6 because this is I'm using notes from a different teacher, and I had a different section of it. So here we're going to show that show how to find a solution y equals fx to a differential equation. In this lesson, all we're doing is we're just approximating a solution to the differential equation, and this approximation is called Euler's method. So we have a slope formula, which is 1 plus y, and here we see a slope field that we're trying to do is we're using this slope formula to help us figure out order pairs along the curve. Now here I drew out what the actual curve is going to look like, but we're not after the actual curve. We're based, we have limited information, so all we can hope for is that we can get something that will look like this, and that's all we need. And so we have number one showing us here's a slope formula. Here's what the slope field looks like. We kind of have an idea how the graph is moving just by looking at the movement of the curves. And then they tell us an anchor point on the function y of 0 equals 0, delta x equals 0.5. So this tells us this is the step size for our function. Okay. So what we're going to do is we're going to take the order pair. We're going to take the slope formula. From the slope formula, we'll be able to kind of have an idea how we want to move. And then once we have that point figured out, then we'll identify that point, and then we'll plug into the slope formula again, move again, find that point, move again. So the dy dx just basically tell us the slope, so we can use it to kind of map out our step along the way. So using this method, we're going to show an approximation to the curve y equals f of x. So again, this is what the actual curve looks like, and our curve should look something like that after we gather enough information. So step one is construct a tangent line at 0, 0 for a function between 0 and 0.5. So here's our tangent line equation. Now we have our ordered pair to begin with. So we have 0, 0. And then from this point, we can also use it to figure out what is the slope at that point, right? So our slope is our dy dx, our dy dx at 0, 0. It's just plug into the formula. I get 1 plus 0, which is 1. Okay, we create our tangent line equation. We have order pair being 0, 0. So we say y minus 0 is equal to 1 times x minus 0, where basically y equals x. So with that tangent line from 0, 0, we know our, now we're not going to do this every time here. I just want to kind of show you that this is the process, but we're going to have a much more efficient way of gathering information. Okay, we know our slope, our equation is x. We know that equation is going to look like this. And then if we follow that line to 0.5, we're going to land at 0.5. So after we create our tangent line and our slope, we're going to have an idea where to point. And if once we know where to point, then we can gather the next point that we want to use. So the next point that we want to use is 0.5, 0.5. And then from this point, we're going to gather the slope, find the tangent line equation, figure out what that tangent line equation is. And then from there, we'll be able to draw a slope segment to the next point that we're after. And then we just keep going. Okay. The smaller the step, the more accurate we're going to be. The larger the step, the less accurate, because we're gathering less information over the process, over the course of this problem. So no, we don't have to worry about how accurate we are. We just have to do whatever the problem tells us. If it tells us do it in 4 steps, we'll do 4 steps. If it's 3 steps, we'll do 3 steps. Okay, so we'll repeat the process. Now that we're at 0.5, we're going to create a tangent line based off of this, and then we're going to find what the slope tells us at this point. Okay. So we're still using the same slope formula. Now the slope formula only needs the y value, so I have 1 plus 0.5, which is 1.5. Okay, so we have our ordered pair, we have our slope, we do point slope form again. I'm going to skip some steps here. My equation is 1.5x minus 0.25. So based off of this slope and from this point, we're going to find out what our next point is. So our next point is 1 because we already found the point at order pair at 0.5. We're going to find the next point is also 0.5 over. So we'll plug 1 into this linear equation here. And that lands us at 1.25. So from here, it goes to 1.25 at the next increment over. And each time we go gather information, it's kind of following along the our slope field, and it's also looking similar to what the actual graph looks like. So our starting point before was 0.5, 0.5, and now we've progressed to 1.25. And we should repeat the process again. We take our new order pair, plug into the slope formula, get our slope, create our new tangent line equation. We create what that segment looks like, use that tangent line equation to get our next point until we reach what we're trying to find. We're trying to find what is, using this approximation method, where's the graph sitting at in terms of the y value at when the x is 1.5. Okay, so taking our new order pair 1 and 1.25, we plug into our slope formula, we get 2.25. We take our order pair, we take our slope, create our tangent line equation, plug 1.5 in using our new linear approximation method, and then our final approximation using this method is at 1.5. The y value is 2.375. Now, this is not going to be the exact point on the curve, but this is our approximation based off of the number of steps that we're asked to do. Now, if we were to decrease the number of steps, then we're gathering more information. As we gather more information, this will become more accurate. But again, we don't have to worry about like this is accurate versus this by how much. You just have to be able to know that it's an approximation and use the method to help us find that approximation. That's really all we need to be concerned with this section. Okay, so the main idea with Euler's method is that by using multiple tangent lines with updated slopes along the way, then the approximation of the point on the solution curve will be closer to the actual value. And again, the smaller the step size, the more accurate the approximation.
Is there a way to make the steps infinitely smaller?
If we did that, then it would no longer be an approximation. So the whole purpose is that we're able to get a pretty accurate read of the function because maybe we're unable to solve the differential equation because we don't have enough tools to do it. So we're able to get at least some approximation that is what's better than linear approximation. And that's just basically repeat the linear approximation multiple times over the course of this process. Now, this is a little cumbersome here with, it's not hard, but it's just cumbersome in terms of writing out all this, having to create, use an entire page just to go through an approximation of this multiple times. So we're going to condense the process into a table of values. And that way we can just gather our information a lot more efficiently. And that's what we want to be able to do on the AP exam because we don't want to spend 10 minutes on one problem. We want to be able to move through a problem quickly so we can just get what we need, provide the answer, and move on. But I want to show this step to you first because I want you guys to see the big picture that we're really just doing linear approximation over and over again as we move along our. Okay, next page. Now, this is a little long here. So I think after we go through one or two steps, well, actually, maybe it's worth it to go through it, even though this is a little bit longer than what you're going to have to do on the quiz or test, but maybe it's good just to have us get into that, get that practice in. So here's a way that we want to be able to show or to gather our information. First, our dy dx, that's our slope formula, right? Let f of x equal to y be a solution for this differential equation. If f of 1 equals 3, that's going to be your starting point. That's going to be your anchor point to begin with. It says, what is the approximation of f of 2 obtained by using Euler's method with 5 steps of equal size? So first thing is we want to figure out what is our step size. Okay, what is our step size? And our step size is going to be using this formula b minus a over n because we want every step to be the same, equal subintervals. So our a and b value are going to be your x value. We're starting at x equals 1 and we're ending at x equals what? 2. So that's our a and b value. So we'll say 2 minus 1 divided by 5, which is 1/5, which is 0.2. So each time we're going to create, if the table is not drawn for you, then we'll just draw our own table. So your table is going to have 4 columns. You're going to have x, a y prime, and your new y. And what I sometimes do on my table here is I say x and I say y sub 0 to indicate that's going to be my starting y value. You can say y prime or dy dx. Here you're gathering your slope information. And your new y looks like this. Your new y is going to be y equals y sub 0 plus y prime delta x. This is just a rearranging of this equation here. Maybe in a more efficient form, so we don't have to write out all this, but you have y minus y sub 1 or y sub 0, that's rearranged in this form. Your m is your dy, your y prime, and your x minus x1 is your delta x. That's going to be your step size. So really, we're just writing our tangent equation in a different form, but it's the same thing. Okay, so what's our anchor point? What point do they give us? 1, 3. Okay, so and then our step size is 0.2. We want to eventually make our way down to f of 2. So let's just go ahead and fill out our x values along the way. We're going to keep adding 0.2 until we reach our destination. So 1.2, 1.4, 1.6, 1.8, 2. We're going to gather each information. As we gather more information, we'll find a new updated y value, and then we're just going to keep building off of that point. And then our goal is to reach this point. Once we reach this point, then that's going to be our approximation. So we're not going to use these boxes here. Okay, so we're just going to go from left to right. As we gather our new information, we're going to copy that down here and just continue repeating the process. Okay, so you can go ahead and have your calculator out if you like. Our y prime is our slope formula. This will always be given to you. So here my dy dx is 2x. Sometimes your derivative may require both the x and y value. You're just going to take whatever information they need from the table, from the row that you're on, and then just plug in. So here, the derivative only requires an x value. So 2 times 1 is 2. So my y prime is equal to 2. So I'm going to take my slope. I'm going to take my ordered pair. I'm going to use that to get to my new y value. So my new y value is y sub 0. Y sub 0 is just whatever y value you're on at that moment, plus the slope and delta x. That's going to be your x sub 2 minus x sub 1. Okay, so 3 plus 0.4 is 3.4. This is now the new y value that I found, which is going to be the starting y value for my next step. So you're going to copy whatever you find here, you're going to copy it down to the next row. So now we repeat the process. Y prime or dy dx is 2x. Now we have a new x value to involve. My new slope at this point is 2.4. Then we go through the same process again. We take our y value that we're on, we adapt another slope at that point. along with the delta x to get to our new y value. So we're gathering information, figuring out the slope formula for that, and then we're just inching along the way, making adjustments based off of what the curve slope information is giving us. So it's not hard, it's just a little tedious having to repeat the same process over and over again. And y prime is 2 times 1.4, get that slope. And again, once we get to the stage here, all we can say is this is just some approximation. We don't know what that exact y value is, but we're able to provide the information, the approximation that the problem wants us to find. Okay, let's go to practice problem number 1. Table below gives value of f prime, the derivative of f. If f of 1 equals 2, what is the approximation of f of 2.5 obtained by using Euler's method with 3 steps of equal size? This one is a little bit nicer because they're giving you f prime. We don't have to do we don't have to do as much calculation, but still similar. So I'm going to create a table here, 4 columns. I have my x, I have my y sub 0, I have my f prime or dy dx or y prime, any of those, whatever notation they give you, you can use that. And then my new y value is just using tangent line to get to it. So it's going to be y sub 0 plus the slope. In this case, my slope is under f prime times delta x. So you can call that dy dx. You can call this y prime or f prime. So whatever you want to do there, but okay, let's find your delta x. Your delta x is b minus a over n. We're starting at 1 and we're ending at 2.5. So that's your a and b value. And then your n is the number of steps. Here we want 3 steps. Oops, sorry, 1.5. No, 2.5 minus. My bad. Okay, so our step size is 0.5. Start off with your starting point there. So 1, 2. Step size is 0.5. So next is 1.5. We're ending at going to 2 and then to 2.5. So we're ending here. Okay, so y prime, f prime at 1 is 0.3. So that's my slope. Einstein equation to get to our next order pair. Take that value and copy it down to the next row. Next up, I want to find f prime of 1.5. F prime of 1.5 is 0.7. Take your updated y sub 0. Take your new slope, your delta x, and get your updated new y value. Copy that new y value to the y sub 0 in the next row. Next up, I want to find f prime of 2. F prime of 2 is 1.2. .1, and that's where I stop. I just want to know, what is f of 2.5's approximated y value? Okay, let's do one more where the problem looks a little bit different, but pretty much, if you understand this process, it's just going to repeat itself. Nothing really new. But I want to show you one problem where the derivative may be given in a different, looks a little bit different. But so if you guys turn to page 18, and let's go to number 5. Okay, page 18, number 5. Same thing, it's just that we have to kind of find the derivative on our own here, but it says number 5, page 18. Use Euler's method to starting at x equals 1 with 2 steps of equal size to approximate h of 3. That's my b value. And my n is 2. Okay, delta x, b minus a over n. I'm sorry, 3, my bad, 3 minus 1. Okay, so my step size is just 1. Okay, so I'm starting at 1. I don't have the y value, but what do we have to help us find that y value? Yeah, the function, right? So let's use the function to help us find our anchor point. What do you notice here? The bounds are the same, so my y value is just going to be what?
0.
Just 0, right? So this one we kind of have to start on our own. We do need an h prime, or I call it f prime here, but we do need h prime. So h prime, I want to find the derivative of this notation. What does this remind you of? Yeah, got that second theorem right. You know, derivative integral will cancel each other out. So we kind of had to find the slope formula on our own. So drop the integral and derivative notation, replace the x in for t, but everything else is going to stay the same, right? There's nothing that needs to be done. Okay, so there's my slope formula. If I want to use proper notation, this really should be h prime times f delta x. Okay, so now we're just gathering information, right? We have our step size being 1. We want to go from 1 to 2, and then from 2 to 3. Okay, h prime of 1. Let's get to my slope here. Copy the new y value to the y sub 0 on the second row. Repeat the process. H prime is just root 1 plus 2 squared. So hopefully you guys find this pretty easy. I think the only challenge here, I think, is just make sure you memorize how to build your table. Right? Every table you're going to create has 4 columns. You have x, y sub 0, your derivative column, and then make sure you know how to get to your new y value, which is just y equals mx plus b, basically, right? But rearranged in a way so that you know how to pull that information. You got y sub 0, you got your slope, and then you have your delta x, and then your step size formula delta x equals b minus a over n. If you know that, then it should feel like a simple process. It's just a little bit tedious, but it's not too hard. Any questions? All right, I just want to show you real quick of this one type of L'Hopital's rule that we haven't quite seen. So if you guys can turn back to page 14. Okay, L'Hopital's rule, just a quick reminder. If we're evaluating a limit and we get either 0, 0 or infinity or over infinity, that gives us the green light to do L'Hopital's rule. So L'Hopital rules just says, rewrite your numerator and denominator as derivative expressions and then reevaluate and see if that will get us to a number where before we're getting something that didn't quite work out. Okay. So I want us to look at a form that doesn't quite fit into L'Hopital's rule initially. And that is something where we basically have a variable raised to a variable. That's the only scenario that I want us to look at. I'm trying to find an expression that is in the form of a variable raised to a variable. That doesn't quite fit into L'Hopital's form because we need a numerator and denominator, both showing either 0 over 0 or infinity over infinity before we can do L'Hopital's rule. So the challenge here is just try to get it into this fractional form so we can actually perform that limit and actually get to this so that we can do L'Hopital's. But when something is not quite in the form, we have to do a little bit of cleanup. And the cleanup process is log differentiation. We're just taking the log of both sides to force that exponent to come down to make it a little bit easier to manipulate and rearrange. So let's just look at example 2, part A. So first, we see a variable expression raised to a variable expression. We're not able to do L'Hopital's rule in this form, even though we are getting infinity raised to the infinity. So, or sorry, 1 raised to the infinity, but basically this is still a variable raised to a variable. So what we want to start off with is let's just write out the equation as y equals. Let's just explore this function, see if we can get it into a form that is more usable for us. So if I want to play with this right side in terms of how this looks, a variable raised to a variable is hard to work with. What if we take the natural log of both sides? That exponent is now free to come down. Okay, what can I move here? The x, right? So x comes down. Now, this is still not quite in the form that we want. We want a numerator over a denominator so that we can actually find the limit, and we're hoping to get producing indeterminate form so that we can actually do L'Hopital's rule. So this requires some manipulation here. We can't move this natural log easily, but maybe I can rewrite the x in terms of something that lives in the denominator. So multiplying by x, going backwards here, multiplying by x is the same thing as dividing by what?
1 over x.
1 over x, right? So we're forcing that denominator to show up in this form so that we can actually get something like 0 over 0 or hopefully infinity over infinity, one of those two options. And I'm not going to do examples A and B, so I'm going to move up to this page. Now, let's do what the limit problem tells us. We're going to ignore that natural log of y on the left side. We'll deal with that when we resolve the right side here. So let's test out infinity to see what we actually get. If I plug infinity in for the x, 2 over infinity is what?
0.
So that just becomes 1 plus 0. What's natural log of 1 plus 0? Is 0. Okay, 1 over infinity. 1 over infinity is basically 0, right? 1 over a really large number is going to be a really small number, 0. So again, I like to use arrows here because if it's free response, AP graders don't like to see equal sign. So now that we have 0, 0, this is now a candidate for us to use what? L'Hopital's rule. L'Hopital's rule, I want to find the derivative. To find the derivative, I'm going to rewrite my expressions here to get it ready for a power rule that can show up within the u prime over u or derivative. Okay, so I'm going to do derivative rule here, numerator and denominator separately, and then reevaluate. So u prime over u, I get negative is negative 2x to the negative 2 over 1 plus 2x to the negative 1 all over negative 1x to the negative 2. Let me do some cleanup here. Maybe get this cleaned up before we reevaluate our limit. Right, dividing by a fraction is the same thing as multiplying by its reciprocal. I left it in that form because I want as long as I can get them to look alike, so I can cancel them out. That's all I care about. So now let me reevaluate the limit. Oh, sorry, the two negatives cancel out, positive. Sorry, positive 2, positive 2. Okay, so now limit as x approaches infinity. 2 over infinity is going to be 0. Now I'm able to get down to a real number, right? So this is equal to 2. Right, so now we got to worry about that, right? So the right side is resolved. We got the limit being equal to 2, but we haven't solved for y yet, right? This is just natural log of y. So then we go back and we say natural log of y is equal to 2. And then raise both sides with e as the base. And we're able to get to our new adapted limit after we undo that limit log differentiation process.
E squared is the limit.
Yeah, e squared is the limit, right? I know we only got through one of these examples, but we'll practice we'll do more practice of this. But the process is you take the natural log of both sides, get it into a numerator denominator, confirm that it's indeterminate form, L'Hopital's rule, reevaluate, and then resolve that natural log of y at the end. Okay, come get your phones. Check your calendar for your homework. The ones I give you will be, we're just looking at this specific case for the quiz.